All right. Good morning, everyone. Let's get started. So, all right. Is there any question before we get started? Okay. So I would like to go over the syllabus today because we did not go over that last time. So this is the course syllabus, course information, textbook. Again, the textbook, you should buy the regular edition, not the international edition, because that one will miss out on homework problems. Course outline, we will try to follow this, but not, strictly. So the schedule may deviate from this a little bit. Um, Great breakdown. So homework, you will be assigned weekly homework from the text. Your homework will be graded 80% on completion. 20% the grader will look at, how you do the homework, how decent you do the homework, that kind of thing. But mostly, if you complete the homework, you should get at least 80% of the score. Quiz is a glorified name for homework, actually. So quiz will also be assigned weekly. You have 1 week to do your quiz and 1 week to do your homework. So after the lecture today, I'll assign quiz and homework on Canvas. You have a week to do so, all right, until next Friday, due at the end of the day. Written scanned submission. Quiz will be graded, okay, definitely on precision, right or wrong. Basically, there are extra problems that I think are worth doing, and also things that I would kind of want you to do on your own, because I'm aware that solutions, right, to the homework from this text is posted, right, on the internet. But I strongly discourage you, okay, from just copying solutions. If you want to pass this class or do well, copying solutions definitely is not the way to go. Midterms, 2 midterms, 1 final. The midterms will be, and the exams will be during class time, because this is a synchronous class. It will be live, so we will use lockdown browser, and you will have to turn on your webcam, your camera. I will provide more details, okay, as we get closer to the first midterm. Basically, you do a live exam like you would do in class. Headset problem. What do you mean? Oh, I'm just going over the syllabus. All right, and so no, you will have 1 page of note. Okay, I will detail that later. So not open note, but you can bring your one formula sheet or cheat sheet where you can put your own information there. There's some restriction, so you cannot put everything on like small font, that kind of stuff. But the point is, I want you to choose, okay, pick and choose what you want to memorize and what you want to put down on papers. All right. So one thing I want to mention is the weight, like, is like this. There is a column, okay, on your canvas, okay, grade that I think is called total column or something. That automatically is calculated. That's calculated with equal weight. So do not look at that as an indication of how well you're doing in this class, because students will tend to do well in homework and quizzes. And if they're equally weighted, then your average will look higher than what you really get. I should change that, but I can't. I couldn't figure out how to delete that column or change the weight. So it's just there, okay? But do not look at it. I mean, if you want to calculate your own total, then follow, right, the percentage that I put down here. Missing exam, academic honesty, that kind of thing. If you are to miss any assignment, okay, the preferred mode of communication is let me know beforehand. I'm pretty flexible as long as you have some, legitimate reasons, including technological difficulty, sickness, that kind of stuff, we can make an arrangement. After the fact, it's just a little bit harder for me, okay, to justify everything. Midterm date, final date, midterm dates, final date, I haven't found the schedule yet, so I think we'll, again, right, put that down as we get closer to the time, to the date. So that's basically it, okay, about the syllabus. Any question on this? Okay. So before we start, I want to put out an announcement. There is a study group. There's someone in the class looking to start a study group for students who feel underprepared for probability. All right. I mean, in terms of probability. So if you're interested, feel free to contact, and then the person will, hold on, let me see if I can see the chat. There's some chat going on. I can't seem to see it. Oh, 1 second here. I can't seem to see the chat. Sorry. How the heck do I see the chat? Sorry, did someone say something? Can you speak in the microphone? I just cannot bring the chat up. Oh, okay. Yeah. Okay. Yeah. Yeah, Jake, I didn't want to kind of, name your name, but if you want to put down your email or something so people can contact you, then yeah. Okay. So as mentioned, probability is a strong requirement, okay, for this class. So you need to be prepared. All right, cool. All right, so let's start. So let's begin with the context of statistical context from last time. Okay. So we're still in review. Okay. So basically, for those of you who, well, you should have watched the first lecture. So chapter 1 to 7, okay, especially 3 to 7, are the review on probabilities in this textbook that kind of encapsulate, probably all of the probability knowledge that we'll be using, okay, later on in this class. So this week we're going through these materials and kind of highlight the tools that I think will be relevant, and of course with examples that are relevant to statistics. But if you want to test yourself on this knowledge to see if you're prepared, well, homework this week will be assigned in these chapters, and you can see if you're comfortable with these problems. And okay, so we're doing review, but also again tying with statistical concepts. So let's start with this. All right, let's do what I call baby stat, meaning what you might have seen when you took a elementary statistical course. You're given, all right, a sequence of number, given, let's say n numerical values, okay? Let's say, again, 100, 105, 110, 90, okay, 120, etc. Okay. So n, of course, right, is the sample size, how many numbers you have. And this may be, let's say the weight, okay, of some female population. From some female population. Okay. Now, what you would do in this kind of context, right, is you compute some so-called sample, right, stat. Right, you have sample mean, median, max, min, mode, range, right? That kind of stuff. And I think that most of you have seen, right, what these concepts are and have done some calculation, right, by hand on these concepts. For example, right, X bar, the sample mean will be here, right, 100 plus 105, etc., right, plus 120 divided by 5. Okay. So I call it baby stat because basically you just run numbers, you do some plotting with it, whatever, right? There's no probability involved if you think carefully about it. I mean, there's some probability behind the scene, but you never really invoke anything probabilistic. So us, right, math stat for 81, we kind of take this context too, because this is the stat, really the stat context starts with a sample. But math stat, right, start with this, that the question is, okay, these are weights of some female population. What is the model? Okay, what is the probabilistic model? Okay, now the word model may scare you, but basically it's the random variable that we mentioned before. But when you think about it, right, that's the model you impose on this data. And okay, without kind of like, let's just pick something. And let's say the answer is something like, okay, let's say they are normal with mean mu and variance sigma square. Okay, where you would say that the mu and sigma square are both unknown. All right. So what you're saying, right, is that these, right, so above, right, the above, what I have are 5 values, which I denote x1, x2, up to x5, right? Notice I use little x for constants, okay? So down here, right, what I'm thinking is I really have, in the background or model, 5 random variables, big X1 to big X5, okay? Each of these are, right, independent of each other, because it's just like sample from independently. They are identically distributed because they're all, right, coming from the same distribution family, which is, or from the same model, which is the model with mean mu, normal with mean mu and variance sigma square. Okay, and so the term independent, identically distributed will be used over and over again in this class and in many other courses. So they will be abbreviated, okay, as IID, okay? Whenever you see IID, that's what we mean. Independent and like same distribution. And, right, of course, the connection with the above is that the little x1, x2, right, x5, these are realized value, right? These are realized value. Of the random variable, okay? The realized values of the random variable. So what we're interested in, right, are the big X, not the small x, because we're interested in the probabilistic, okay, properties of, this random sample. So for example, right, we are interested in, so above, right, you have little x bar, which is a number, which is a realized value of big X bar, which is the sum of xi divided by 5, right? I equals 1 to 5, or in general, the sum of xi, I from 1 to n divided by n. Okay. So the big difference, right, is big X bar now is a random variable. Okay. While the little x bar above, as you are used to do in statistics, right, baby statistics is a number. So for us, right, we look at big X bar from the point of view of being a random variable. All right. And so we are interested in, right? So we are interested in studying, right, the properties, okay, of big X bar. For example, okay, from the given sample model. In other words, right, our model is that all these x's are normal, which mean mu and sigma square. Well, what is X bar then? What distribution does X bar have? Okay, what other things can we say about X bar? So the point of view, again, right, the point of view is this. That above, right, is after you have seen, right, the trial, you have done the experiment and you see these numbers and you just do your calculation. This is very routine. The point of view here is we take an abstract point of view, right? This is a more theoretical point of view, which, by the way, right, all statistical studies are based on anyway. That, okay, that before you do the experiment, you have a model in mind, all right? What do you expect in terms of the experiment on how this, so-called statistics behave, okay? X bar, right, is a sample statistic. What do you expect? Okay, these statistics, how do you expect these statistics behave before the trial? Okay, so before the trial, right, all statistics are random variable. You do not know what the value, how the trial will come out, okay? But you have a model. You can say probabilistically, you expect this and that to happen, okay? Again, what are their properties? Also, another point of view is, right, this is in theory, but you never expect to do an experiment and call it a day. Meaning, right, you do a drug trial and you say, okay, I got the result. I don't want to think about it anymore. In theory, right, the whole point of you doing the experiment is that this experiment can be repeated again and again and again and again. Each experiment, right, each of these 5, for example, each time you collect 5 weights from the female population, it's clear, right, that these 5 ways will never repeat, right? There will be always different numbers, all right? But if they all come from the same population, same distribution, then they consistently have some kind of properties that you can say, all right? So in other words, they are always the realized value of this big X bar, okay? That you can say something about. For example, on average, okay, it's about this value, its spread, its variance, it's so and so, all right? So also, right, experiments can be repeated forever, right? Experiments can be repeated, right? And should be repeated, all right? And each time the outcome of the experiment, each time with different outcomes. So therefore, right, taking the point of view of a numerical values is a very elementary point of view that you do not want to take when you study advanced statistics. Because advanced statistics is about, again, right, studying probabilistic properties of the statistic itself, all right? So any question before we continue? Okay. 90, sorry. Okay, that's just, all right. So now another comment before we continue, all right? So what is statistics? Okay, what is a statistic? What is a statistic? All right. So statistics with an S is the name of a field of study, right? But statistic without S actually has a meaning, okay? Has a name, has a meaning, has a definition. So basically a statistic, right, is a function any function of a sample. Okay. So in that sense, right, for example, again, you have x1, right, up to x5. When you form the average by summing all these guys up and divide by n, by the way, right, I will be in very much of the habit of when I write the sum like this, without writing the lower sum, the lower limit and the upper limit is always from 1 to n, all right, because that's almost always the only sum that we talk about in this class. When there are potentially different meanings, I will spell it out, okay? But when I write the sum like this, almost always, because writing 1 to n every time is kind of really cumbersome, this always means sum from 1 to n, all right? Right, the sample mean, right, is a function of x1 to x5, okay? Another one, when you think about it, let's say the sample max, okay, which is the max of all these guys, again, is a function of x1 to x5. All right, so statistics with an S as a field of study, right, is a study of these guys. This is a study of function of random sample. It's a study of properties, right, of these ones, right, function of the samples. Of course, right, you don't want to take any arbitrary functions and study. The reason why x bar, for example, or the max, right, are meaningful or always highlighted, because this says something about your model, okay? The relevant statistics, right, there are probably some so-called irrelevant statistics, meaning they're function of the sample, but they don't tell you anything you care to know, right? So the popular, right, the popular, right, or the well-known, right? What by that I mean the mean, the max, the median, the mode, etc. Tell us, right, some information about the model, okay, of the distribution of the population. Okay. So for example, right, and I think this is well known to everyone and it's obvious that when I say, right, that the 5 female weights that I sample come from, let's say the model is normal mu sigma square. Okay. When I form the X bar like this, it says something about the mu, right? Or in other words, a very popular, right, notation is mu hat is equal to X bar. What I mean by that, and which we'll talk about later, all right, not today, but just mentioning the idea, mu hat meaning an estimator for mu, okay? In the absence of any, right, further knowledge, I say my best guess, or not best guess yet, but my guess, right, for the value of mu will be the sample mean, all right? And I will also have some guess, right, for the value of sigma square with the sample variance, etc. So by computing, right, the statistics, it will shed light, right, on the model. So this process also is called calibration, right, by the way, model calibration. Now, one thing, right, when we say model, right, inherently what we say is we're not even sure that this is the truth, right, which actually entails even the question of is even the normal assumption appropriate, okay, which is valid to ask. But the point of view, okay, of parametric statistics, or at least the point of view of this class, is we don't question the distribution, the family of distribution. We take that as correct. Of course, that's very questionable, but we don't question this. We accept, right, that the model, right, at least the family distribution is okay. We just say, okay, so accepting that assumption, what are the sensible things to say about the parameters, okay? The parameters are always unknown, by the way, okay? So pay attention to that. I will emphasize that later. The parameters are unknown, and we perform, right, statistics to say something about the parameters. And from the properties of the statistics, we can say something about how well, okay, our estimators perform in terms of guessing this unknown value. Okay, that's more or less the story of the whole semester, actually. Okay, so that's that. And again, right, because these are all random variables, so using probability, right, to work on them is a must. Probability is a tool, is the tool for us, okay, to study the statistics. That's really it. So if you don't have the tool, you're stuck. Any question? Okay. So now let's really go back, right, to where we stopped last time, which is the moment generating function. Okay. And again, the theme, right, of the whole discussion last time, and actually the theme of the class too in some way. And the one question that you will do very well to always keep in mind when you study this class or anything close to probability is, what does it take to know completely a random variable? Okay. Because, right, for example, the sample mean, I form it, all right, from doing this operation from some model. What do I know about it? Okay, what can I say about it? What does it take for me to know completely about X bar? Meaning I know everything that needs to know about it, all right? And of course, right, completely is a very demanding question and ambitious, and sometimes we just cannot know completely about anything. So we have to settle with partial knowledge. But right, at least the question of how to know it completely is, right, the answer is to describe its distribution, okay? And this is an abstract word to say, right, either the right probability, right, distribution function, if it's discrete, or, right, I mean the PDF, if it's continuous. Now, of course, all right, that sometimes if the distribution is well known, and this is the point of studying, right, well-known distribution, which is, I think, a part of chapter 5 and chapter 6. Hold on. Yeah, chapter 5 and 6, right? So we can also, right, we can also just name it. With well-known distributions. Okay, so the point of chapter 5 and 6 are for this. For example, right, in the above example, I have x1, okay, up to xn, IID, normal mu sigma square. All right. Again, so to repeat, right, the idea. And by the way, this will be a very quickly, very routine thing that we will keep writing again and again this class. What I mean is I have a random sample of n values, of n random variables. They're all independent. They all have the same distribution, namely they're all normal mu sigma square. Okay, that's what I mean. Now, right, then I form the X bar. All right, and the biggest question, right, that concerns me is what is X bar? And you know, this tilde, right, means distribution. So X bar tilde question mark means what is the distribution of X bar? All right, and I will give you the answer right now, which says that I have described completely, and now I explain why I can do that. The answer is X bar will have normal with mean mu and variance sigma square over n. All right, that's it. And exactly that, right? That's what I mean by name the distribution by well-known, right? So I don't need to tell you the density because, hey, that's too pedantic. Everyone can look up the normal, right, if they want to. Here, right, I say this and I'm done with my task of completely identifying, right, the X bar. Is that okay? Of course, right, part of the task of the class is to explain why I can do this. But right, as far as the question is concerned, saying this means I'm finished with the answer. Any question? All right. So then, of course, right now, the main point, right, one of the big work of the class is why. Now, the why, right, is really tricky business because remember, right, probability is a tool. When you have a question, you just kind of search in your toolbox and find the best tool. Best means the most convenient tool to solve the problem, okay, to establish why it's true. The best tool, right, is, of course, you can quote a result. The result is something like this, right? Sum of independent normal is normal, okay? So the mathematical statement, right, a more rigorous statement would say X is normal mu1 sigma 1 square, Y normal mu2 sigma 2 square. X and Y are independent. Remember, right, this notation means independent. Then X plus Y is normal mu1 plus mu2 sigma 1 square plus sigma 2 square. Okay? So again, right, there's an English statement, there's a mathematical statement. They're both equally valuable. The English makes the intuition clear or more digestible. The math makes it pretty precise. Okay? All right, so of course, you can quote this, and of course, if you quote this, then the above statement is perfectly clear. Independent. It's like orthogonal, it's like that notation orthogonal. Orthogonal in geometry. It has that meaning too. All right. Now, do you agree that after I establish this, then this is clear? Well, why? Because, right, if x1 up to xn, IID normal mu sigma square, then what distribution does the sum of xi have? Applying this result. Sorry, apply this result. And by the way, right, these are the things that you should be able to do very quickly. And that's what I mean by having your probabilistic background. Yeah, sure, normal, what kind of mean, what kind of variance? N times mu, very good. What about the variance? Very good, n sigma square, very good, right? But that's not it, right? Because the object is x bar. So x bar is this sum divided by n. So what distribution does it have? Normal, right, with mean mu and variance sigma square over n. Where, right, we quote two results. We scale in normal, it still stays normal. That's a result, right? We talked about before. Remember, right, scaling a random variable does not necessarily stay in the same family, all right? Scaling a Poisson doesn't stay Poisson. So here is a not trivial result, but fine. Another one, right, is something like this. That's C, right, expectation of Cx is C expectation of x. Variance of Cx is C square variance of X, where obviously, right, the C I have in mind is 1 over N. Is this okay? Clear? I hope I take that as a yes. But all right, and again, right, you may be a little bit rusty on this, but right, these are not new results, and the level operation of switching, right, between this kind of knowledge, this kind of calculation is exactly, again, right, what I mean by familiarity with probability. All right. But so this is easy stuff actually, right? And this is not even what I mean by the why yet. So this y has another y behind it. Okay, y is a sum of independent normal. In other words, why is this true, right? So I quote this result as a tool to prove a result about my statistic, about my sample mean. But it's very legitimate to ask why this is true by itself, okay, as a probabilistic result. And again, right, by the way, even though this class is statistics, that doesn't mean independent probabilistic result is not relevant, because, right, sometimes the work of statistics is to establish the probabilistic result you need to use, okay? So now another y, okay? And this y is this one, okay? The y of this. Okay, so this y is a little more complicated. This y can be established, right, via moment-gen function. Okay, and this is back to what we discussed last time, where we say moment-gen function uniquely identifies a random variable or a distribution. By the way, right, so this will be my abbreviation for distribution. So that, again, right, this statement add another step to the toolbox. What does it take to know completely a random variable? You can either give it distribution function, which is kind of cumbersome, density, also painful, name them, okay? Another one is give it MGF, all right? When we say this, we imply that all of these are equivalent. Do one of the following, and I shut up, meaning I'm satisfied, okay? You have answered my question. All right, so for example, how do we carry this out? To carry the scheme of MGF out, you must be familiar with the MGF of a family, all right? So you need to know MGF of a family. Now, this task usually is very fun to prove or to compute, but sometimes you can take the higher point of view by look up in Wikipedia. All right. So there are certain things that at some point you take them as formulaic calculation and you don't bother. But of course, you know, once in a while, if the mood suits me, I will do calculation, because sometimes the calculation is the point actually. Okay. Here, the calculation is not so much a point, because I want to demonstrate the idea of MGF uniquely identifies a random variable. So I will quote result. Okay. But so what result is relevant to us right now? The result is about the normal MGF, right? The normal MGF. By the way, right, I keep saying MGF. What's the definition? The definition, right, is an MGF of a random variable at a point t, right? X is a random variable. MGF is a function of t, all right, of a constant scalar, is defined by expectation of e to tx. That's the definition. Of course, right, after you unravel this expectation, right, using the formula, you will get a function of t explicitly. And that's the point of looking up on Wikipedia or your trusted source of reference. So, oh, by the way, right, Do not confuse this with, no, so I should not use F, right? Because F is a notation for density. Should I use phi or something? Maybe that would not, right? Confuse that with F. Phi, okay, phi for MGF, because little f is kind of used for density, all right? So, okay, so normal MGF means if I have an X with normal mu sigma square, what is the MGF of X? Does anyone know? Again, right, these are MGF knowledge is a little bit more technical. Only if you're a little bit more dedicated to probability would you commit this to mind. So don't worry if you don't know it. I'm just curious if anyone has this in mind. Again, right? Excellent, excellent, exactly. Wow, we have a probabilistic enthusiast among us. That's correct. So yeah, or you can always look up on Wikipedia. nothing wrong with that. So exactly either t mu plus 1/2 t square sigma square. Okay. So therefore, right, let's see what it takes to use this result in the y that we asked. The y was, right, x1 is normal mu1 sigma 1 square, x2 is normal, oh sorry, x, right, and then y, you can do x1, x2 too, doesn't matter. Mu2 sigma 2 square, right? I claim that they're independent. I claim that x plus y is normal mu1 plus mu2 sigma 1 square plus sigma 2 square. Now, because MGF uniquely identifies a random variable, and because I know that a normal MGF takes this form, it is enough for me to establish that the MGF of x plus y will be at t will be e to the t mu1 plus mu2 plus 1/2 sigma 1 square plus sigma 2 square, t square. If I can establish this somehow, this is to be proven, but if it can be proved, then I'm done. Then this automatically follows, because these two facts are equivalent. These two facts are equivalent. MGF uniquely identifies a distribution. Okay, any question on how this fits together? Fit together. All right, we're okay. Question. Feel free to, if you feel typing too slow, you can speak in the microphone, right? I mean, I have no problem with that right now. All right, so okay, so then of course, how to establish this? Okay, how? The how is actually a very beautiful, right, property of MGF. If x and y are independent, then phi, the moment generating function of the sum, is the product of the moment generating function. Okay. And then of course, like this is why, right, math or probability is so annoying. You can keep asking why until eternity. Why? Well, why is because, right, what is this? This by definition is expectation of e to t x plus y, exponential of e to t x plus y, exponential of t x plus y. Now, obviously, by property of exponential is this. But because x and y are independent, these two being deterministic functions of x and y are also independent. Therefore, by property of expectation, right? And by the way, again, right, I was quoting a very easy property of expectation. Expectation of a product is a product expectation. when they're independent. And so we recognize that this is phi x of t, phi y of t. Hence the result. Okay. But then, right, you recognize that because of this formula, this part right here is exactly the MGF of x. This part right here exactly is the MGF of y. And when you multiply them together, the exponent add. So the formula can be proven exactly by this piece. And that's it. Okay. Any question? You want to say something, Derek?
Yeah, can I ask a question about something a little before?
Mm-hmm.
Can you explain where you got the sigma squared over n?
Yeah, exactly from this formula. Because, right, what is variance of x bar? Variance of x bar being variance of the sum over n will be 1 over n squared variance of the sum, right? Exactly by this property. But what is the variance of the sum? The variance of the sum is n sigma squared, as we established above. Therefore, this is n sigma squared over n squared, which is sigma squared over n.
Oh, okay, thanks.
Mhm. Any other question? All right, so the purpose of this demonstration is not just to impress you with MGF and that kind of thing. The purpose is to show you that MGF is a tool, right, to establish some result that you will just use in quote so casually in statistics. All right, and of course, I think those of you who kind of seen something further know that from here you get the confidence interval, okay, the Z alpha over 2 confidence interval for the mu, exactly also from this. But you see, right, the whole machinery behind justifying something like this, all right? It's not that we will drag this in every time, right, we see X bar. We will just keep quoting this. But, right, the point of knowing behind the scene that this is the reason is that if somehow your assumption is modified, you can think about whether or not this still follows or what changes, what not, that kind of thing, all right? So I'm very practical in terms of my knowledge, in the sense that I want to establish a coherence in reasoning why things work in certain ways. So, right, I'm not doing this for fun, meaning, oh, it's so beautiful. Of course, it's beautiful by itself, but in terms of the value, right, to help you understand the properties of the statistics, all right, namely the sample mean in this case, is the point of the discussion, all right. Okay, so that's moment change function. Any question before we move on to the next topic? By the way, right, so this will be used in the T distribution chi-square and F later on, okay? So again, I'm not doing this for fun either. The MGF will come back when we study this distribution later on. All right, so if there's no question, then let me move on to the next topic, which is the joint distribution. And function of joint distribution. Okay. So joint distribution, by the way, so where do you see this? I think this is in chapter 7. So when we say joint distribution, hold on, let me make sure it's right. Also chapter 3. So chapter 3 and chapter 7. Chapter 3 discuss the joint distribution, and chapter 7 talks about the function. All right. So joint distribution means, right, that if you have a collection of x1, x2, up to xn, not necessarily IID, okay, just a collection of random variables, the joint density, right, the joint density or the joint distribution, right, if they're all continuous, will be denoted as fx1, x2, right, up to xn of lil x1, lil x2, up to lil xn. Okay. The most popular one you will see is something like fxy of xy when n equals to 2. Right? So this is a two-dimensional version. All right. It describes the joint behavior of x and y as random variables. So two things that will be relevant for us in the future. One is very easy. In the case when x1, x2 are IID, okay, how does the joint distribution look? How does the joint density look? So, okay, so maybe let me do this too, right? If they are discrete, okay, if these guys are discrete, then you would do joint distribution if they're discrete. So let me erase this. So these are the continuous case, right? If discrete case, you would have joint probability function, maybe. Meaning you would say something like probability of x1 equals to some value, x2 equals to some value, xn equals to some value, right? Like this. That's when they're discrete. Okay. So now when x1 up to xn are IID, all right, when x1 up to xn are IID, how does the joint density look? The joint density, okay, so first of all, because they are independent, the first I, the density will be product of individual density. Okay, like so let's say fxi of xi, I from 1 to n. So this is from independent. Okay. The second one is because they're all identically distributed, the second I. All this function will be the same function. All this function will be the same function. So you will drop the xi and you just say one single x. Of course, you cannot raise this to the n power yet because the argument inside each of these functions are different because they are individual values of the random variables. But the point is that the density function will be the same because they're identical. Okay. So the x here, right, represents the population distribution, the same model that they all come from. All right. For example, in the above, right, example we discussed, when we say x1 up to xn IID, normal, mean mu, variance sigma squared. Then the joint, right, the joint density function, all right, will be product, right, I from 1 to n of individual density evaluated at lil xi. Here, the densities are the densities of the normal. So it will be 1 over square root of 2 pi sigma square, same sigma because they're all identical, again, right, same family, e to the minus xi minus mu square over sigma square, like that, okay? So that's where you start. And then you can do some manipulation to make this simpler. For example, you can say is equal to 1 over 2 pi sigma square raised to the n over 2 e to a minus sum of xi minus mu square over sigma square. And this is a typical form of a joint normal, independent normal distribution that you will see. And I skipped the argument here, right, because it's just too cumbersome to write. But this, for example, right, is the joint density of IID normal. Okay. Any question? This will be very routine and very relevant when we use, right, very routine. I would say routine, you see it like thousands of times when we discuss likelihood function. Okay. So maybe let's give you an example for this discrete. Okay, so these are all, this is a random sample from a Poisson lambda family. Then I need, right, and I will switch to this notation called L, all right, L for likelihood. For all intent purposes, it's just a joint probability distribution function like this, okay? But I will switch notation to L because that's what we use later on. It's called likelihood, okay? Likelihood function. So L of lil x1, x2, up to lil xn will be what? Will be the product, okay, of individual probabilities. So I from 1 to n. What are the individual probabilities? This is Poisson lambda. The probability it takes on a particular value lil xi is e to minus lambda, lambda raised to xi over xi factorial. Again, you can stop here, but typical, cleanup decoration might lead you to something like e to minus n lambda, lambda raised to a sum of xi over the product xi factorial, like that. Okay. Any question? And so, right, the point of me mentioning this is because, again, this will be used again and again and again later on. But basically, what I want to highlight here is the structure and the form, right, of random variables. One discrete, one continuous, and we look at them together as a joint behavior, right? Even though this is an easy one there can be. They're all independent and they're identically distributed. But there is one single object, right, called the joint distribution that capture their combined behavior probabilistically that we need to manipulate. So you want to understand, right, why we do the product, for example, from independent, why we can simplify stuff down to the same formula because of the identically distributed, all right? And then we operate from that angle on, okay? And again, right, the basis of it is all probability. So being super familiar with the families from chapter 4 and 5, right, is very important because you see how I just quote this, distribution right out of my mind. Of course, again, I worked on this like, all my entire life or something, but because these are the things we use again and again and again in this class. Being that much familiar with this formulation will be very helpful for you to move on with the argument, right? That's down the road These are just the preparation, right? We write this down and we start studying them. It's not like we spend like 10 minutes staring at this to figure out why the formula is true, etc. Right? We take this for granted. Okay, any question? Another one, okay, which is a little bit rare, but actually is very, very popular when you study probability, but it's a little more rare in this class. There is one time you will use it, but all other times. But I want to mention this because it's quite important. The transformation, okay, the topic of function or transformation, okay, or distribution of transformation. So the idea is this, that if you have x, y, okay, as a pair of random variable with joint density given, and you do a transformation to u and v, okay. A typical example involves something like u equals to, let's say, x plus y, v equals to x minus y. I think you have seen that before. Or, product and division, that kind of thing. But, right, clearly when you do this, right, this is called transformation, like calculus 3 transformation. This is still a pair of random variable. Well, what is the joint density here? All right. And usually it's really a tedious thing to work out if you don't know what you're looking for. Because, right, the transformation is not that, simple to unravel like the one-dimensional case that I worked out for you last time with the chi-square, right? The chi-square is very, very standard manipulation. But this one, right, because of the nature of a 2 by 2 transformation, is a little bit more hairy. So for this, I want to call your attention to the following formula, theorem 7.2, okay, on page 218. Anytime you feel like you're in something like this situation, feel free to look it up and quote the formula. And trust me, quoting the formula itself is a little bit more challenging already. All right, let's not even get into the intuition. The intuition is not that hard. But I want to focus, right, on how to apply this result, and I'll tell you, where it's applied later on. But be able to apply this result, right, this transformation, which, by the way, I think you should have seen that in 4 and 7, is important, okay, for some application that we'll do in this class. So let me quote the result, okay? Let me quote the result. The result says this, that the density of u and v, okay, will be the density of x and y, but with x in the form of u and v, y in the form of u and v, sorry, little x, little y. And multiply with something called the determinant of the Jacobian in absolute value. Okay, where the Jacobian is the matrix of partials, partial x over partial u, partial x over partial v, partial y over partial u, partial y over partial v. Okay, where here x and y are inverse function. The reason is you're always given u and v as function of x, y. Here you're asking to, resolve that. You ask to solve x in terms of u and v, and you ask to solve y in terms of u and v. Okay, and then determinant. So again, right, I would not expect that you can immediately digest this formula and see what it means. And trust me, the text formula is even a little bit more weird than this. I do this in terms of my notation, but the text formula is a little bit more, they add some more notation. But I will demonstrate an example for you, all right, and hope and help you to see what's entailed here and how it's used. That's what I care, right, for. Again, right, the point of having a mastery of probability is you can use the formula when it's spelled out for you in the correct way, at least. So an example I want to demonstrate is this. I want to revisit that example we just did, which is, let's say x is normal 0, 1, y is normal 0, 1. Okay. I want to say that x plus y has normal 0, 2 distribution. And of course, they're independent. Okay, they're independent. So I simplify this because, if I introduce mu and sigma square, it just makes the calculation very, the symbols very tedious because we're working at the density level, all right? And it makes you appreciate the MGF approach. The MGF approach is super clean. But I want to demonstrate this approach to you so at least you see that there are many ways to solve the same problem, okay? And so the point is, right, we will do this via the density approach, okay? We will do this via density approach. In other words, right, we'll do something like this. We want to say that if I call x plus y to be u, all right, I just give it a name. Then the density, right, of u will be, right, being a normal, right, 0, 2, it will be 1 over square root of 2 pi, right, sigma square, so times 4, e to minus x, e to minus u square divided by e to minus x squared over sigma square over 4, like this. Okay. So I want to establish this by density approach. Now, those of you who have worked on the sum of random variables will appreciate that calculating density of the sum is not a joke. All right, it's not. It takes some time. The trick is I want to demonstrate that I can use this theorem to just come out with the result. Okay, I will use theorem 7.2. Okay, I will use theorem 7.2. How would I do this? Because notice, right, theorem 7.2 says, one of the tricky thing you may wonder is, how can I do this? Because this says x, y goes to u and v. Here, right, so basically this is u, this is correct, but where's v? You don't have v. Well, don't worry about it because, right, you can always invent a v to go along with your calculation. And then when you have the joint, you can just guess what the marginal is. So maybe let's just invent the v to be x. Let's choose that. Make the transformation easy. All right. So the what do I want to say here, right? The formula, right, gives me the joint density of u and v, all right, in terms of the joint density of x and y, and then the term of Jacobian. So let me try to figure out, right, what is the joint density of x and y. The joint density of x and y, being standard normal, independent, is exactly, right, the joint density that we just wrote above, is 1 over square root of 2 pi for the x, e to minus x squared over 2, 1 over square root 2 pi, e to minus y squared over 2, like that. Okay. Now, then I need to look at the Jacobian, right? The Jacobian will be, okay, so hold on. So let me do this, right? I need to look at the inverse function. So u is x plus y, right? And v is x. So solving for the inverse, right? That means that x is equal to v and y is equal to u minus v. Is that okay? X is equal to v, y is u minus v. All right, so in terms of the Jacobian, it's very easy because the Jacobian, by the construction, makes all this calculation very easy. Partial x over partial v is partial x over partial u is 0. Partial x over partial v is 1. Partial y over partial u is 1. Partial y over partial v is minus 1. All right, like this. So the whole determinant of the Jacobian absolute value is just 1. Nothing to worry about. All right. But then, right, the challenge is for me to, okay, so then I will need to plug in here, right? And I need to plug in the joint density. So the formula tells me that the joint density of u and v will be, right, exactly this formula, but plug in, right, v for x and u minus v for y. Keeping the same, right? Let's do this. E to the minus v squared over 2, e to the minus u minus v squared over 2, like that. Okay. And then determinant of Jacobian is 1, so I don't need to worry about it. Now, what do I care for? What do I care for? I want the density of u. Okay, I want the density of u. So I'm not sure if I'm in some trouble here because here is a joint density of u and v. Okay, here's a joint density of u and v. I need to integrate out. So I think I'm not giving you the easy example possible. The final step is I need to integrate out all the v to get to the density of u. All right. It's not an easy integration because I have the v here, okay, on both sides. It's not an easy integration. So maybe this is not the easiest thing to demonstrate that, right, the density of u is this. But at least I hope that this is an example to show you how to go from the density of a pair of random variable, u and v like this, right, x and y like this, to a pair of random of u and v, okay? With following the formula 7.2 from the textbook is really one of the more challenging topic in this course, all right? But being able to read this formula, all right, do the calculation and transforming like this will be useful at some point in the course, all right? And I want to point out where we use this. Okay. Later on in the course, when we have x1 up to xn like this, we will be able to derive the density of the max. We will be able to derive the density of the min. And in some way, you can derive the joint density of the max and the min. One quantity of special interest, okay, to statistics is called the range, meaning how far you think the distribution goes. The range will be the max minus the min. So the textbook will ask you to find the density of the range, the distribution of the range. Okay. And so you see the range being the difference of the max and the min will intimately involve the joint density of the max and the min. And so you must use this formula, or at least the easiest thing for you to use, is this theorem right here to work out the joint density and then integrate out. Okay. Again, one of the messier topic in this course, and I think that one of the messier topic in 477 as well. But it's super important that I just need to mention this. All right, and as painful as it is, we'll need to do this once in this class as well. So the point again, right, is you are able to carry out that formula in that theorem 7.2 in this way as I described. Okay. So any question about how I go from here to here using the theorem is my question for you. You all go to sleep already with all this math? Don't blame you. The question is, do you have any question following the steps here? And the steps here, I just mean implementing this result. You should have seen this in 407, all right? So I'm repeating some old material in some way. But I know that this is one of the trickier part of 407 anyway. So being able to implement this kind of procedure is the question. Like I was doing this example, any question on this example? On how I can plug in this and that. What is even the point of this, right? The point of this is to derive the joint density of U and V from this relation from the joint density of X and Y. The ultimate goal is to derive only the joint density, only the density of U. But I was pointing out that it involves a messy calculation of integrating out the V. This is called the marginal, right? This is called the marginal density. Okay, so just maybe rehearsing concepts that you should have seen before. But the main point, the main highlight is going from here to here. Any question on that?
How did you pick the V equals X?
Good question. That right, in this whole scheme of thing, in the big scheme of thing, is a trick, right? Because our ultimate goal is to pick the U. So you pick some convenient V to make it easy to calculate. For example, calculate the Jacobian, right? Sometimes, and this is what makes probability super hard, there's no right choice for V. Actually, V could be this too, and maybe the form will be nicer, I don't know. Like V could be X minus Y. It could be nicer, I don't know, right? But a standard choice is just to pick something easy so that when you do the Jacobian, it doesn't mess around with the calculation. Does that make sense? But yeah, there's no justification on me choosing B. It's just an easy choice so that I can go down and calculate. So an exercise for you should be try this with U equals to X plus Y and V equals to X minus Y and see what the result comes out, for example. And I think I will put down a quiz question for you to figure out on this kind of stuff coming up. All right, so we're almost out of time. Let me say, right, there's two more topics I want to touch on before we start discussing statistics. Of course, right, among too many topics, but one is called asymptotics. In other words, central limit theorem and law of large number. Another topic is just basically working with densities. in a quote unquote quote smart way. So we'll discuss this, all right, in class on Tuesday. So, all right, if you want to leave, I won't keep you. I just want to highlight, all right, the topics that I mentioned in a systematic way. That like just recap what you need to know, okay, from probability, and then after we finish this, we will do statistics proper. Yeah, thank you, Christine. So recap, right? What you need to know or want to know. Density, the concept of density, joint density, the concept of distribution, joint distribution. This is chapter 3. 2, the concept of expectation variance, MGF, okay, with its entailing properties, and this is chapter 4. Oh, by the way, let me throw in covariance too, chapter 4, okay. Transformations of random variable. This is chapter 7. Very, very familiar with basic random variables. This is chapter 5 and 6. All right. And then 5, the asymptotics. In other words, central limit theorem. And these, I think, are somehow buried in somewhere. So let me say just, class or, old book. Okay. So if I have to break down the topics, it's like this. If you're very familiar with all of these topics, you're in good shape. All right. So thank you for joining. Sorry for keeping you. I will post homework and quiz soon. All right. They're all due next Friday by the end of the day. All right. Have a good weekend, guys. Thank you. Thank you. Thank you.